Hello, this is Ms. Nichols, and this is the third lecture in the magnetism unit. The topic is magnetic force, and the essential question is, how do we determine the size and direction of the magnetic force? Probably won't surprise you that we're going to use an F sub m to represent magnetic force. And if you remember our discussions about forces, you remember that every force is an interaction between pairs of objects. So magnetic force is no exception. It is an interaction between a pair of magnets. This can be any kind of magnets or any combination of kinds. So it can be a permanent magnet interacting with a current carrying wire, etc. They can all interact with each other. There's some examples of different kinds of magnets interacting with other kinds of magnets. The units of magnetic force, because it's a force, are in newtons, and of course this is now becoming a new force that we can add to free body diagrams in combination with all the other forces that we've learned about: electric force, normal force, buoyant force, etc. A reminder, because it's always good to get these reminders, Newton's third law says that every force is equal and opposite on both objects. So whatever the two magnets are involved in your interaction, the magnetic force is going to be the same on each of them in opposite directions. The equations to calculate magnetic force due to magnetism are very situationally dependent. In other words, like if we had a permanent magnet, to calculate the magnetic force from it, we'd have to know all the dimensions of it, the degree to which the domains were magnetized, etc. That equation is way beyond, or those set of equations would be beyond the scope of this class. So this class is only going to mathematically be able to handle two very specific magnetic force situations. And the first is the magnetic force that would act on a current carrying wire, an electromagnet, from some kind of external magnetic source field. So in all of these problems, we're just going to assume the second magnet is kind of outside of the problem, and we already know the magnetic field from that source magnet, and we're really only going to be focused on the effect on the test magnet. So this would be a sample situation where, see that B is the external magnetic field. We don't know what it's from, we don't care. What we do see is the current carrying wire that we care about. Please note that B shown is not the magnetic field from the wire, right? We learned how to do that in the last set of lectures with the first right-hand rule. That's not shown in this picture, and the reason is because the wire's own magnetic field does not affect itself, right? You have to have two objects. That's how we have an interaction. So the wire is in a different object's magnetic field, and that would be the setup to find the force on the wire. There are three relationships that are going to determine the magnitude of the force on this wire. The first is that the magnetic force on the wire will be linear with the current going through the wire, which makes sense since magnetism is caused by moving charges. The more moving charges you have, the more magnetism you're probably going to experience. Magnetic force is also linear with the source field. So the stronger the second magnet is, the stronger the magnetic force. And then the third relationship is that the magnetic force is going to be linear with the amount of the wire that's in the field. You'll see in this picture that is shown, L is just the chunk of the wire that's in the field. That wire extends past that magnetic field. We don't care about that. That's not the part that's going to be interacting. All we care about is the L inside the field. So given these three linear relationships, the equation is actually pretty straightforward, although it looks a lot uglier on your equation sheet than you would be led to believe, because there's a lot of absolute values, and those little arrows on top just tell me what the vectors are, which actually is important as well. But in any case, there's one thing in that equation that should stand out as a little bit different, and that is this sine theta. So what on earth is sine theta? Well, theta is the angle between the wire and the magnetic, or the current, and the magnetic field from the source magnet. And so the fact that that appears in that equation should tell you something kind of weird is going on, that we care about the angle between those two vectors. And in fact, if you dig a little deeper into the mathematics and you think about when would that sine theta value be at its maximum and when would it be at its minimum, it actually tells you something kind of profound about magnetic force. because if the current in the wire is parallel to the magnetic field, in other words, theta is 0, the wires are in the same direction or anti-parallel from B, sine theta is 0, and that tells me that Fm is also 0. In other words, a wire carrying a current parallel to a magnetic field actually doesn't experience any magnetism. So there is no magnetic force between those two magnets if the current is parallel to the external field. And so in that example, those two wires shown in green at the top, those wires actually experience no Fm because they're in parallel with that magnetic field. On the flip side, sine theta reaches a maximum if theta is 90 degrees. In other words, if the wire is fully perpendicular to the magnetic field, that's when we get the most amount of magnetic force, as shown by that third wire in the diagram. So we're going to come back to this in a little bit. Of course, you could calculate the amount of magnetic force at different angles between 0 and 90, but most of the questions in the test just want you to know those two kind of extreme scenarios. When do we get a maximum force and when do we get a minimum force? So like we discussed in the last video, the equations or the magnitude is actually the easy part in magnetism. Usually the most conceptually challenging part is figuring out what is the direction of the magnetic force on that current carrying wire. And it's particularly tricky because there are actually 3 vectors in this magnetic force equation. The 3 variables that are vectors are magnetic force has a direction, B, the magnetic field, the source field has a direction, and I, the direction of the current. We're going to consider L a scalar for the purposes of this. And that's really strange because in most physics equations, there's always only been 2 vectors, like F equals ma. F is a vector, A is a vector, M is not. And the rule up to this point has always been when there are 2 vectors in an equation, they're always in the same direction. So if you push an object this way, it accelerates that way, always, always, always. And it's sort of been a rule of thumb. So how do we deal with this when we have 3 vectors in the equation? What do we know about their direction? Well, the really, really weird thing about magnetism is that, in fact, none of those vectors are in the same direction. They're actually mutually perpendicular with each other. And we'll talk a little bit conceptually why in class, but for now, I'm just going to tell you the what, which is that if one of those vectors is in the x-axis, another one must be in the y-axis, and the third must be in the z-axis. We can't have 2 that are parallel with each other, or there basically is no magnetic force. So to determine the direction of those 3 vectors, we are going to bring in a second right-hand rule. For the second right-hand rule, again, you need to put down your pencil and pick up your right hand. The difference on the second one is that you don't do any kind of curling or bending. You actually hold your hand as straight as you can make it, kind of like you're just sticking it in a glove. And so this is how you'll do the second right-hand rule. In the second right-hand rule, you are going to point your thumb in the direction of the current through the wire. So that's the same as the first right-hand rule, which is handy. So take your thumb, just like it's a hitchhiker. Where are you going? Point your thumb in the direction that the current is moving. Do remember that current is positive flow. So if you have negative flow, or they tell you which way the electrons are moving in the current in the circuit, you actually need to point your thumb opposite from the direction of that. The second part of your hand is going to be your fingers, okay? So you can see how your fingers are perpendicular to your thumb, which makes this handy. Your fingers are going to be pointing in the direction of the external magnetic field, okay? So in the last problem, fingers were magnetic field, but they were the field from this wire. In this problem, it's still field, but it's the field from another magnet. So that's a little bit of a nuance. But in any case, fingers, they kind of look like field lines, so fingers point in the direction of the magnetic field. And then the third vector is going to be an imaginary arrow popping out of your palm. And that is going to be the direction of the force on the test magnet. So imagine a force coming out of your palm. And note, that is the force on the test magnet. Okay, the source magnet would experience equal and opposite force, but this is going to tell you the force on the wire. So let's run through a couple quick examples. That one on the top, right? First we'll do the top one. Pick up your hand, okay? The current in the wire piece that is shown is going to the right, so you want your thumb going to the right, okay? The magnetic field as shown is going up. So actually, remember, on your paper, up is like towards your computer screen at this point, right? So you want your fingers going towards your computer screen, and then you should discover that the force, or your palm, is popping out of the paper, which means that wire will experience a force out. In the second example shown down below, current is going up, so take your right hand and rotate it so your thumb is pointing upwards on your paper towards the screen. The magnetic field is going to the right, so you got to rotate your hand around until the magnetic field, your fingers are pointing to the right. And then if you look at where your palm is, your palm should be pointing into the paper, which is why that force is shown with an X going into the paper. So hopefully your right hand agrees with those two diagrams. The second equation that you have on your equation sheet to describe the magnetic force on a magnet is for the magnetic force on a free moving particle. And again, we're going to be experiencing magnetic force from some kind of external magnetic field. So this diagram shown is very similar. We have the B, which is the magnetic field from some other source magnet. And down at the bottom, we have that little charge, positive Q, and it's currently moving upwards, as you can see shown by that V vector. The relationships in this equation are actually very similar. They basically parallel the ones from the last equation, so I'm going to go through them pretty quickly. Fm is now going to be linear with the charge of the particle. So the more charged the particle is, the stronger the force. Again, Fm is going to be linear with the source field, and then Fm is going to be linear with the velocity of the particle. The faster that particle is moving, the more magnetism it is going to be experiencing. The equation looks basically the same as the last one, except we substitute Q and V in for I and L. We have the same sine theta, which tells me again, if the velocity of the particle is parallel to B, we have no magnetic force, and if it's perpendicular, that's when the magnetic force is at its maximum. You're going to use the same second right-hand rule to find the direction of these vectors. The only little bit of a difference is thumb, which was pointing the direction of positive current, is now just going to point the direction of positive velocity, which should make a lot of sense. So, for example, in shown, magnetic field is coming out of the paper, so put your fingers out of the paper. Rotate your hand so that your thumb is pointing up on your paper, and you should find that your palm is showing that we have a magnetic force on that particle to the right, if you've used your right hand. Okay. Remember to flip the direction of your thumb if it is an electron. This is actually relatively common. Usually for the electromagnets through wires, they tell you current, which is already positive. But for free moving particles, they love to throw an electron in there instead of a proton and realize that your thumb has to be pointing in the opposite direction for it to work. So again, fingers point the same as they did last time, external B field, and palm will tell you the direction of the force on that particle. Something pretty interesting about free moving particles in magnetic fields is that those particles will always undergo what is known as centripetal motion. Centripetal means circular. And a definition for this is basically that a free charged particle is always going to be traveling in a circular arc-shaped path when it is in a uniform magnetic field. If that particle is completely inside of the magnetic field the whole time, it's just going to go in a circle. This is orbit. This is the same as gravitational orbit, essentially, except for using a magnet to do it instead of using Earth. So that particle that is moving is just going to keep going in a circle. The reason that it does this is because since we just discovered that right-hand rule, magnetic force by definition is always perpendicular to the velocity. it's not going to speed the thing up or slow it down. You'd have to be pushing in the direction it's moving or counter to the direction it's moving to speed it up or slowing down. Pushing or pulling sideways to the motion, all it does is causes an object to turn. This turning of objects without speeding up or slowing them down is called centripetal motion, and it is an acceleration because the velocity vector is changing. Even though the magnitude is not changing, the direction of the velocity is changing. And there is actually an equation on the equation sheet that we will be using for any time we have centripetal motion. A couple other images that can demonstrate this circular motion. This is a pretty common situation where you fire a particle into a magnetic field through like a slot, so it doesn't show beforehand, but that particle is moving straight in through that slot. But as soon as it gets into the field, it is then going to travel in a circular path because, as you can see, the force on it is always perpendicular to the direction that it's moving. You could also have an example of, this is more complicated physics, but if the particle was moving sort of at a weird angle instead of exactly perpendicular to the magnetic field, it would travel in a helical path, which is circular in one dimension. That's beyond the scope of the class. I just thought it was a cool image. So one thing that you should be able to do in this class is realize that the radius of the path that is carved out by that particle depends on variables that we can explain and predict. You could actually calculate the radius of that path. I haven't really seen that come up very often, but I want to give you guys the tools to do that in case you need to. So this is my example at the top. A particle is being shot into the magnetic field. Magnetic field's in that kind of gray area. We don't know the direction of it. I'm not going to worry about that. But you can see that two different particles, A and B, take different radius paths. And so the question is, what could be different about those particles, or what could we use to calculate the radius of a path that a particle would take? So the equation that is on the equation sheet that describes centripetal motion, oh, I'm sorry, that first equation is just Newton's second law, right? We know that any acceleration is equal to sigma f over m. So that's just the definition of acceleration. The new equation on the equation sheet is in the motion portion, and it says A sub c. That stands for centripetal acceleration, and the centripetal acceleration will be equal to the velocity squared of the particle divided by the radius of the path that it carves out. So you can use this anytime an object is moving in a circle, but for our purposes, we're only doing this in magnetism. If you take a different AP class, you'll find all sorts of uses for this for orbital geometries and strings, spinning yo-yos, and things like that. Any case, so we've got these two equations that are going to be relevant. If you were trying to solve this problem, then the first thing that you would do is, as always, when we're dealing with a forces problem, draw a free body diagram. For that particle entering the magnetic field, based on the path that it carves out, I know that the instant it enters the field, it's experiencing a magnetic force to the right. That's the force that's going to eventually turn it, right? That force is going to change direction as it turns, but at the instant it enters the magnetic field, it's experiencing a force to the right. And if that's the only force on that particle, if the other forces are negligible, gravity and electric force, etc., don't make a big impact on this, then we can go ahead and solve for sigma f, right? That's pretty straightforward. Sigma f is the same as Fm in this case because it's the only force. And we can essentially combine those two equations above. Since each of those equations solves for A, I can set those two equations equal to each other, right? So here's what I've done. The left side is the Newton's second law portion, sigma f over m, and sigma f is QVB. I don't need the sine theta in there because it is sine of, the angle is 90 degrees, therefore sine theta is 1. So QVB divided by the mass of the particle equals the v squared of the particle divided by the radius of its path. If we're interested in the radius, which is usually what you're concerned about, you can now solve for r, and a couple of things kind of cancel out, and we are left with r is equal to Vm over QB. This is not an equation given to you on the AP exam. Mostly I want you to have this equation because I want you to understand the relationships that are in it, right? Because V and M are on the top of that fraction, that means there's a linear relationship between the velocity of the particle and the mass of the particle and the radius of the path, and there's an inverse relationship between the charge of the particle and the magnetic source field and the radius of the path. All of these relationships should be somewhat logical, and you're going to get conceptual questions about how R would change when you sort of change something about your experimental design. So for example, in that picture shown, you might easily get a question about what's the difference, or what could be the difference between particle A and particle B. So given all these relationships, particle A has a smaller radius. That means it could be slower than B because there's a linear relationship between velocity and R. If we're going slower, right, we're gonna turn in a smaller radius for the same force. A could be lighter than B. A very light particle would turn on a very small radius. Or, on the flip side, A could have more charge than B, because if it's a higher charge particle, it's actually going to get more magnetic force from that field, and it would turn tighter. Or, of course, if we somehow are changing the magnetic field, A could indicate a stronger external force field. So, in any case, all of these relationships come out of that equation, but you should just be able to explain them sort of conceptually. All right, we're at the end of the video. Please revisit your essential question and write down any questions you've got about how we determine the size and direction of magnetic forces. Thanks for watching.